Hello everybody and welcome to another video. Now in today's video we are going to be talking about one of the most popular tests when it comes to hypothesis test and statistical inference. I'm talking about ANOVA, and that's the short form, while the full form is analysis of variance. Yeah, exactly. I used to think it's analysis of variation, but I don't know. I think it's analysis of variance. So basically, this is one of the most popular tests in statistics and it has several types. And in today's video, we are going to be learning how to perform ANOVA in SPSS. Now, there are several types of ANOVA out there. I think we have like 6 or 7 of them, but we can't perform all of them in SPSS. We can only perform like, I think 4 of them in SPSS. So I will take my time right now to explain all of the several types of ANOVA and move on to SPSS to actually perform this ANOVA, the 4 types that can be performed using SPSS. So first thing first, the full meaning of ANOVA is analysis of variance, and it is a statistical test that is used to test for the difference in means between groups, at least 2 groups. Now I use the word at least 2 because there is actually a statistical test that we can actually use to test for the difference between the means of 2 groups, and that is the independent sample t-test. But what I'm trying to say right here is that sometimes the ANOVA can actually replace the independent sample t-test. Now basically we actually have like I said earlier on, we have like 7 types of ANOVA, but the most popular type of ANOVA is what we call the one-way ANOVA. So the one-way ANOVA is actually the ANOVA that we use to compare the difference between the means of at least 2 groups. So the one-way ANOVA works like this. We have a dependent variable and we have the independent variable. So your dependent variable must be continuous in nature. By continuous, it means that it is measurable and it can take decimal value. And your independent variable, also known as the factor variable, must be a categorical variable and it must have at least 2 levels. So a typical example of one-way ANOVA in action is if I'm trying to test for the difference in exam score between 3 faculties. So let's assume we have 3 faculties. Let's say Faculty of Science, Faculty of Engineering, and Faculty of Management Science, and they did a test on mathematics. Okay, so the test score in this case, okay, is the dependent variable, is the yeah, it's the continuous variable right here because it can take decimal. Now, the independence variable, aka the factor, is actually the faculty, and in this case of ours, it has 3 levels. That's Faculty of Science, Faculty of Engineering, and Faculty of Social Science. So if I'm interested in testing for the difference between the math test score rather across the 3 groups, I'm going to be making use of the concept of one-way ANOVA. So put that in mind. For one-way ANOVA, we have just one dependent, one independent, and the independence must be categorical and it must have at least 2 categories. Now, the two-way ANOVA is just a one-way ANOVA on steroids in the sense that for a two-way ANOVA, we still have just one dependent variable, which must still be continuous and can take decimal values. And for your independent variables, we have 2 of them. And these 2 independent variables must actually have at least 2 categories. So let's say in this case, rather, we are interested in, okay, the math score between faculties, 3 faculties, and also we add another categorical variable. Let's say we add religion. So we have the Muslims, the Christians, and let's say the, I don't know which religion I can add, but one more religion, let's say Buddhist. So we are trying to see how the math score is varying between the first category of faculty students and the next category of religion. Okay, so in this case of ours, the goal is to see how the 2 categories, okay, like the 2 categorical variables, relate individually with the test score, that is the dependent variable, and also how the both of them combine to also relate at the same time with the dependent variable. So that is the concept of the two-way ANOVA. So we also have the repeated measure ANOVA, and the repeated measure ANOVA is just that ANOVA that you perform when you try to measure your independent variable multiple times over a period of time. So the value of your independent variable, your category, is not fixed. It's changing multiple times, it's changing over time. So you're trying to use that to also relate with the dependent variable. So that is a repeated measure ANOVA. So The next is the MANOVA, which is just the multiple analysis of variation of variance, and which simply means that instead of having just two categorical variables as our as our independent variable, you're going to be having three, four, five, like multiple categorical variables. Now, up next is what we call the ANCOVA, which in full means the analysis of covariance. And the best way to explain this is that the analysis of covariance is the combination of ANOVA and regression. So it's actually quite advanced, but I will just keep it as simple as that. Now, up next is what we call the Kruskal-Wallis test. And the Kruskal-Wallis test is just the non-parametric counterpart of the one-way ANOVA, which simply means that one of the conditions that defines the one-way ANOVA is that the dependent variable should follow that of a normal distribution. So if your dependent variable does not follow normality, then you're going to be using the Kruskal-Wallis test. So that is like the non-parametric counterpart of the one-way ANOVA. And then the next one is what we call the Friedman test. Okay, so the Friedman test is the non-parametric counterpart of the repeated measure ANOVA. So before I move into SPSS and start performing ANOVA, I want us to know that ANOVA in general has its test statistics as an F test. And an F test is also an F ratio in the sense that we are trying to get the ratio between two variances. Okay, so now that we've done that, we are going to be moving into SPSS to actually learn and see all of these ANOVA in action. So without further ado, let's get into SPSS. Yeah. Hello everyone. So this is the sample data set that I will be using to teach you guys how to perform a one-way ANOVA in SPSS. So I actually got this data set from SPSS itself. It's like it's tagged as a bank loan data. So what I'm going to do is that I'm going to get this data set for you guys and link it in the description of this video so that you can just check it out and play around with it. So let's just take a quick look at the variables in our data set. So we have age, education level, employment, blah blah blah, and all of those things. So basically what I have in mind for the one-way ANOVA is based on the fact that I want to see if there is a difference in income, okay, based on educational level. So for this educational level, I think it has like 5 categories. Let me check that. Let's just do a bit of a frequency analysis on that, and let's just see. Nothing really much, just this. Yeah, so let's just check that. Okay, why is this taking so long to work on it? All right, so I really don't know why it took that much of a time, but yeah, here we are. So we have 1, 2, 3, 4, 5. We have 5 categories. Yeah, so this is just the basic the basic frequency analysis. So like I said earlier on, the one-way ANOVA is basically used to test for the difference in mean across at least 2 categories. So if you want to perform a one-way ANOVA, what you're going to do is to come to analyze right here, then you come to compare the means, and you come to one-way ANOVA. All right, so let me just take this back. All right, so yeah, so I'm interested in trying to see if there's a difference in income across the level of education. So the income is going to be going to the dependent list, because in this case of ours, our income is the dependent variable. So income right here, so the household income, it's going right there. Then the factor is going to be the independent variable, like I mentioned, and it's going to be level of education right here. So these get into these places. Okay, now you can actually on a normal day, this is unchecked, but I usually advise that you check this, because the effect of size is actually a very important parameter when it comes to hypothesis testing. Okay, yes, your p-value can be less than 0.05, and it tells us that there is this significant difference or something, but the effect of size will make us understand the practical significance of the p-value. So it's very, very important. So I will leave the contrast. I will click on the post hoc. Okay, now we have a lot of post hoc tests that we can use, and we have one for when you assume equal variances, and we have one when we assume for unequal variances. So the best post hoc test that you can use for one-way ANOVA is the Tukey HSD test. Okay, so I will be clicking on this. Okay, now depending on what you want to do or what you want to achieve, you can choose either of this. Some people would choose the Bonferroni over the Tukey. Depends on them. You can also decide to choose more than one post hoc test. It doesn't matter, it's still the same thing. So I'm just gonna go with the Tukey test, and that's all. Then for the null hypothesis, I just leave this as this. Okay, I want to use the same significance level as the settings in the options, and that is 5%. Okay, so if I click on this, it gives me the option to it gives me the option rather to edit this, but I just want to like stick to 5%. Continue. The options, so under the options we have the statistics that we want it to show, and I can allow it to show the descriptive statistics. I can also allow it to show the fixed and random effect. Okay, homogeneity of variance. Okay, maybe not too important, but you can also just click on that. The mean plot, this may not be needed, but you can actually just click on it if you want that. Now the Welsh test is really not needed in this context, but if you would like to do that, you can also do that. Now the confidence intervals for the parameters that we have when necessary, you can also do that. Then you can change this to 99 or 90, anything. I click on continue, and I think we're good to go. Nothing much entirely for us to do, so we click on OK. All right, and then and once you perform your one-way ANOVA, the first thing that you are introduced to is actually the descriptive statistics of income based on educational level. So right here we have that 460 of them did not complete high school. High school degree is 235. Some college is a 101. So the average income for each of them, you have it right. It's like this is just your basic descriptive statistics, and nothing really too much to confuse us. Okay, now you have the test for homogeneity of variance. So the Levenin test is actually the test that we use in statistics to test whether there is homogeneity of variance. Now the null hypothesis of your Levenin test rather is that the variances are actually equal. So we have equal variance, and the alternative is that the variances are not equal. So so based on the mean, the p-value is actually lesser than 0.001. So that means according to all of those p-values right here, everything is actually significant, which simply implies that equal variance is not assumed in this dataset, or should not be assumed in this dataset of ours. That is, this dataset does not have equal variance. The variance across each of the categories are actually not equal. So this is the ANOVA. Very, very important. So this is what we are really, really interested in, and the ANOVA is like the F ratio. Like I said, it's an F ratio, and our test is actually very, very significant. Okay, because it's telling us that in conclusion, it's telling us that that there is actually a difference in income across the 5 groups that we mentioned earlier on. So now the effect of size is actually something that tells us about the practical significance. Okay, so in as much as your p-value might be lesser than 0.05, and you might be thinking that, oh, since I have a lesser p-value or a very, very low p-value, there is actually a significant difference between each of the groups, and you just make that conclusion. Now the effect of size is going to tell you how accurate you are and how practical your results are. So we have several types of effects of size. We actually have the Cohen's d, we have the eta squared, we also have the omega squared. So I think SPSS is giving us four effects of size parameters. We have the eta squared, we have the epsilon squared, we have the omega squared, and we have the omega squared random effect. Okay, I'll be making use of this eta squared, so you can pick one of them. Actually, just pick one, it's fine, there is no big deal. So I'll be starting with the eta squared, and for the eta squared, 0.01 is a small effect of size, 0.06 is a medium effect of size, and 0.14 is a large effect of size. So that is for the eta squared. And for the omega squared, it's also the same thing. 0.01 is the small effect of size, 0.06 is the medium effect of size, and 0.14 is the large effect of size. So based on the eta squared, we can see that we have a 0.05, which is almost close to like 6. So that is a medium effect of size, which simply means that, yeah, to a certain degree, we can actually say that our significance is actually practical in nature. That is, the effect of size, or the significant difference between the income across the groups, is actually practical. For omega, it's still the same thing, to 0.055, which is close to 0.06. So yeah, it's a medium effect. So the reason why we do a post hoc test is based on the fact that, yes, we know that there's a difference between the income across the education level, but which is different? So which of the groups is different from the other? So if you try to come straight to this, you'll see that from those that did not complete a high school, there is really no difference between them and high school. So that means there is no difference between the income of those that did not complete high school and those that completed high school, as you can see from the significance level, yes, which is just a p-value that is more than 0.05. And since your p-value is more than 0.05, you fail to reject the null hypothesis. So this is like a pairwise comparison, which is just a t-test between two groups. So the t-test between this and this, the t-test between this and this, the t-test between this and this, and it keeps going. So if you take a look at from here down here, we can see that all the p-values are actually lesser than 0.05, which simply means that the only guy that is not a difference here is the high school degree, but the rest are actually different. Okay, so you can actually do the same thing for the high school degree and against the rest, for some college against the rest, and you can just interpret it that way. So we can skip this, it's really not important for us. And then this is the mean plot, as you can see. So the mean household income in thousands across, it was plotted on the vertical axis against the level of education, rather. And as you can see, the post undergraduate students or category, they actually have the highest average household income, which actually, makes sense. And this is just how you perform your one-way ANOVA in SPSS. So yeah, we'll see in the next one, and bye for now.